Okay, so today we are going to discuss some kind of a new topic, which is about the mesh deformation. So far in this course, basically what we have discussed are basically some kind of the different representations for the 3D data. And also last week we discussed basically how we can do some kind of the conversion from the one representation to the other. So basically there are some kind of the missing kind of the bridges from the point cloud to the implicit function and also from the voxels to the meshes. And we have seen like how we can do this kind of like conversion from like those representations using the moving least squares and radial basis function, and also the Poisson surface reconstruction and the merchant cubes. So those are basically some techniques that we can do some kind of convergence. And the reasons like why we need to do this kind of conversion is that there are basically some kind of the pros and the cons for those representations. And also what we have seen in the previous lectures is that there are some kind of the good representations in terms of like representing the 3D data to feed those kind of data as kind of input to the neural net. So when you basically feed this kind of data as kind of input to the neural net, like having some point cloud or the multi-view images or the voxels might be kind of the good choice. Right? But also there are some kind of cases that we are generating those kind of 3D data as kind of the output of the neural net. And as kind of the output representations, we have seen that like having the voxels or some implicit function, explicitly like having the implicit function might be kind of the best choice. So depending on whether we want to take those kind of the 3D data as kind of the input and the output, we can consider basically doing some kind of conversion from like one to the other. But basically, there is like one representation we haven't discussed the most kind of the details, like which is the mesh representation. Then what's the point that we are discussing some kind of the mesh representation? So as we discussed at the very beginning of like this course, actually the mesh representation has many kind of the advantages, and which is also the most popular representation, especially in the many compact graphics, the framework. And mesh is kind of the more like direct way to basically represent the surface with some kind of the more explicit expressions, and also in like the very compact way. So when you talk about the mesh, mesh is basically some kind of representation that looks like the graph in terms of that we are having some kind of some vertices and also the edges connecting them. But the difference between the typical mesh representation and the graph representation is that we are not just having the vertices and the edges, but also forming some kind of the faces with some kind of the adjacents, the edges as well. So as you can see in this figure, we are basically connecting the vertices like this with the edges in a way that now we can also have this kind of the polygon the faces that will directly represent the part of the surfaces. So you see the difference between the mesh and the graph representations, right? And also the typical way to have this kind of the mesh representation is to make all those like the faces, not as some kind of the arbitrary the polygons, but as the triangles. So basically having the triangular the meshes is kind of the mostly common the choices for many the graphics the applications. So this is kind of like very compact way to represent the surface, but we can also consider representing not the surface, but the volume as well. So there are also some kind of some volume meshes as well, which is not just having the triangles, but having lots of some connected the tetrahedra inside the volume of this 3D the surface. In terms of that, we can now also represent the volumes with some kind of some vertices, edges, and the faces as well. So those are some kind of very commonly representations. And as we have discussed at the very beginning, there are lots of some kind of the advantages and also the applications that we can do using the mesh representations. For example, like we want to basically render the 3D the data into some kind of the images. Like having this kind of the explicit representation might be much better. So for the rendering the perspective, having the mesh is also very good. For the texturing, to define some kind of color information or some kind of the material information over the surface, also having this kind of the explicit the surface representation might be much better. And also for many kind of some physics simulation, also like the mesh can be basically used in many kind of the simulation the applications. And also for many kind of the manipulation and the deformation of some kind of the 3D the surfaces, having this kind of mesh representation can be really good. The downside of the mesh representation is that we are basically having some kind of the irregular structures of the connectivity of the vertices. So which is quite different with some kind of the typical, some kind of the lattice structure we have seen for the voxel case. So because of those kind of irregular structure, there are lots of some difficulties in terms of like both like feeding those kind of the data representation as the input and also generating those kind of the representations as the output. But as we have seen in the previous slide, once we basically have the other the representation for the 3D data, we can consider converting that into the mesh representation and basically using that for the many of the applications that we have seen in this slide. So this is kind of like very typical the framework, some pipeline in terms of that we are having some kind of the other representation, basically, for example, like making some 3D data as kind of some output using some kind of implicit representation. Then we are converting this into the mesh representation and using that for many applications. So this is like very typical the pipeline for many kind of the 3D reconstruction and the manipulation, the framework. And also we can see lots of some kind of the databases for the 3D meshes. So those are like all the 3D, the mesh databases in the online, including some kind of the databases for some objects like this, and also the databases for some kind of the scanned, the scene like this, and also for the human bodies, or some many kind of things that we can see in the outdoor scenes as well. And I guess so the quite famous the database recent the database the mesh database might be the observers, which is now having some quite huge size, including 10 million the 3D objects with the lots of the diversity and also with some kind of the quite good quality of the 3D shapes. So those are also kind of the 3D objects that are represented into the meshes, and you can use those kind of the 3D models for the many the applications. So you can say that actually the mesh is quite the common the representation for the many kind of the, especially for so many graphics the applications. So given this kind of the loss of some kind of the advantages of the mesh representation, what we are going to discuss for today very specifically is about basically how we can utilize this kind of representation for some kind of the manipulation in terms like deforming the shape. So as you can see, for many of the examples here, we are going to do some kind of the deformation in terms of that, like fixing some part of the shape, while basically moving some part of the other part of the shape like this, in a way that we can make some kind of some naturally deformation of the 3D shapes. So on the roadmap we have seen this slide. Now we are reaching to the mesh representation and also some kind of the ideas about like how we can do some kind of the manipulations for those meshes. Before we get into some more details for the mesh deformation, I'd like to ask you to prepare pen and the paper because we are going to do lots of some kind of the math work tool today. So prepare some the pen and the paper. We are going to have lots of the quizzes. Okay, so let's get into some more details about the mesh deformation. So actually, there are tons of some kind of the techniques for the mesh deformation, and we won't have time to discuss all the techniques for that. So we are going to see like very specific the idea for the mesh deformation, but the very high level the idea for all the techniques for the mesh deformation is that basically we are defining some kind of the objective the function, which is making some kind of the smooth deformation like this, that while basically satisfying some kind of the given the condition. So here basically this is the example that we are having this kind of the plane the mesh, this basically the flat the plane. And we'd like to fix the region, the gray region, the vertices in the gray region at the same position like this, while basically lifting up the yellow region to the up direction like this. And here the question is that we want to make some kind of deformation for the vertices in the middle area, in this like light blue the area. Basically choosing some kind of the new position for the vertices in the light blue the area, while satisfying the two conditions in terms of that the vertices in the gray area should be fixed, and the vertices in the yellow area should be basically moved to the upward like this. So here the question is that how we can define some kind of the objective function for the to choose the some kind of the natural positions for the vertices in the light blue area like this. In terms of that, we can see this kind of some natural sort of the deformations like this. So this is kind of the very high level the idea in terms of like how we are going to do some of the mesh deformation. And there is no some kind of the like one specific the way that we can do this. There are like tons of the way. It's really the matter of like how we define this kind of the objective function to determine some kind of the natural the positions for the vertices in the middle area like this. So there is like huge literature about the mesh deformation in terms of that. So also the techniques can also be categorized into the many other kind of the ways like this. So the first category is about basically directly modifying some kind of the surfaces in the given the 3D mesh. And the other basically the idea is basically about some kind of the based on the cage, which is basically not just directly moving the surface, but basically having some kind of the bounding, some kind of the volumes, including the given the 3D shapes. And then basically making some kind of deformation with these kind of like the bounding volumes in terms of that all the surface inside the bounding volume is also basically deformed following the bounding the cage. So actually, this image is showing some kind of example for the cage-based deformation. In terms of that, we are making some kind of some rough shape, which is including the detailed shape inside it. And then when you basically make some kind of deformation with the bounding the cage, then the shape inside the cage is also deformed in the same way. And also there is some other the idea in terms of that we are defining some kind of a skeleton and doing some kind of the rigging that is connecting those kind of the bone information with the surface in terms of that we can do some kind of the bone-based, the skeleton-based kind of the deformations. So while there are some kind of the lots of the techniques and also lots of the interesting ideas here, we won't have time to discuss everything. So this is actually some kind of the topic that we can discuss in the multiple the lectures, while we are not going to have the time for that. So today we are going to discuss like one specific idea, which is called the as rigid as possible, which is very popular the deformation technique. While if you are interested in some more details for the like all these kind of the techniques, there are also lots of resources for that. I strongly recommend you to check out those kind of the resources. Also, there's like very nice kind of textbook, which is called the Polygon Mesh Deprocessing, which includes like all the information, not only for the deformation, for the many other some kind of mesh processing. And also, if you want to do some kind of more the hands-on the work with the mesh deformation, I also strongly recommend checking out this like libIGL the library, which is also like having all the kind of the code for the mesh deprocessing, which also have some kind of very specific the tutorial for the shape deformation as well. So check this out for the more the ideas and also how we can do like implement those kind of the ideas into the code. So while leaving those kind of resources here, we are going to discuss some very specific idea here today, which is the as rigid as possible deformation, which is also called the Arab deformation here. So as I said, the basic idea for the mesh deformation is like all about basically how we are going to define some kind of the objective function in a way that they can basically determine some kind of the natural the positions of the vertices while satisfying the kind of given the constraints. So this is the basic idea. And for that, the basic, the high level the things for the Arab deformation is that we are defining the objective function in a way that the mesh deformation becomes some kind of the more locally rigid the transformation. So here the point is that what's the meaning of the rigidity transformation? And also what's the meaning of the locally rigid the transformation, right? So I guess everyone would know the meaning of the rigid transformation, right? So what's the case of like having the rigid transformation? What's the meaning of the rigid transformation? Yeah, what are the some specific the types of the transformations that are included in the rigid transformation? So basically, if you move a object in the space, if you are like through a object in the space, that is basically making some kind of the rigid transformation, right? So which is involving only the rotation and the translation. So if you have any kind of like stretching or scaling or skewing, those are not the cases that we are having the rigid transformation. If you just like rotate or the translate the object, that's the case that we are making the rigid transformation, right? So basically, when you talk about some kind of like locally rigid the deformation as much as the possible, which basically means that we don't want to basically make any kind of some stretching or some kind of scaling of the shapes. We want to just like make like all the every the part of the 3D the shape to make some kind of the rigid transformation, which means that we only have some kind of the rotation for the translation for the each part, right? So that's basically the meaning of the rigid transformation. And also the question is that what's the degree of the freedom for the 3D rigid transformations? How many the parameters do we need to express the 3D rigid transformation? Yeah. So we basically need the three numbers for the translation, right? The X, Y, Z, three numbers. And for the rotation, we haven't like we couldn't have the time to discuss like the representations for the rotations, but actually there are also the bunch of the way to represent the 3D rotations. But typically we can represent 3D rotation with only the at least like the three numbers, right? So which means that 3 plus 3, the degree of the freedom for the rigid transformation is basically the 6, right? So yeah, we need some kind of the 6 parameters to represent a rigid transformation. Yeah, but the thing is that what we want to do is that we want to achieve some kind of the local rigidity, right? So what's the meaning of that? We want to achieve some kind of the local rigidity. So for that, basically, we are going to consider how each of these local region is basically deformed with some kind of some given the deformation. So for that, like, there are a bunch of the ways doing this, but we do like to just consider a kind of the warning neighbor of each of the kind of some reference the point. So given any kind of the vertex over the surface, let's consider it's kind of the immediate some kind of the neighbor the vertices directly connected with the edges. So we are having some kind of reference the vertex and some kind of the neighbor the vertices around it, right? So when you talk about the locally rigid transformation, that basically means that for every single some kind of the vertex over some kind of the 3D the mesh, this is basically the case that we can represent the information as some kind of like moving that the reference the vertex into the other positions, and also all the other kind of the neighbor the vertices, their kind of the transformation kind of the new position are basically represented with the single the rotation. So this is kind of the case that we are basically having kind of like the reference vertex, which is the pi, which is now moved to the new position, which is the pi prime here, right? So once we basically the translation is kind of like moving the reference point, the pi to the pi prime, then the positions of all the other the reference the vertices are basically now represented with some kind of single the rotation into some new positions. So basically the changes of the positions for all the enabled the vertices are basically represented with the single the rotation the matrix, the Ri here. So this is the case that we are making is some kind of locally rigid the transformation, right? Make sense? So given this kind of the basic idea, let's say we denote the vector from the pi to the pj as kind of the eij here. So into some kind of the new notation. So let's say the vector for the the ij is basically the vector before the deformation, and the e prime here is basically the vector for the after the deformation. So in this case, like if the deformation is like locally rigid, what is some kind of the relationship between these two? So how can we represent the relationship between these two into some kind of the math form? As I said, like no, this is the case that we are representing the deformation, the transformation for all the neighborhood vertices as kind of some single, the rotation, the rotation matrix, right? So actually the answer is simply basically when you apply the rotation matrix, the Ri to the vector for the H, the Ij here, that should be returning the E prime here, right? The H for the deformed mesh, right? So here, basically, the idea is that we are now looking for some kind of the rotation that can represent the transformation for all the neighbor vertices, right? So the way that we can find such kind of these optimal the rotation for each of the neighborhood might be just like solving this kind of the least scarcity problem, right? So when you basically apply the rotation to the H the vector, the before deformation should be basically aligned with some kind of the vector for the H in the deformed mesh, right? So if we minimize this and find some kind of the rotation that is basically minimizing this, that there will be some kind of the optimal the rotation that can express some kind of the local the rigidity, right? It is clear. So let's just quickly go into this problem in terms of how we are going to find this kind of the optimal rotation that satisfy this kind of some relationship. So when you basically have this kind of like the edges before deformation and the after deformation, how we are going to find some kind of the optimal rotation that is basically representing all this like deformation with a single rotation, right? So this looks like some very simple, some kind of the least scarcity problem, right? The problem is that this Ri here is not any kind of the arbitrary the 3 by 3 matrix. Actually, it should be a rotation the matrix, right? So that is actually making some kind of some lots of the difficulties here. So when the R is not a arbitrary 3 by 3 matrix, but the rotation the matrix, so we know that there are some kind of the conditions that the matrix should be satisfied, right? What are the conditions for the 3 by 3 the rotation the matrix? Yeah, so we didn't discuss some details about this kind of like transformation the matrix in this course. But if we briefly go over with that, actually there are two conditions for the rotation the matrices. The first condition is that the matrix should be orthonormal the matrix, like all the columns and the rows should be basically orthogonal each other, and while the norm should be also the one for each of the row and the columns. And the second condition is that the determinant of the matrix should be +1. If it becomes like -1, that's the case that we are having the reflection matrix. For the rotation matrix, we should be determinant of the +1, right? So there are basically the two conditions. So here the question is that how we can solve this kind of the least scarcity problem while basically satisfying these two conditions, that the matrix should be also normal the matrix, and also the determinant of the matrix should be 1, right? So when it comes to like solving these scarcity the problems with like these two conditions, actually the problem becomes like way more complicated than we expect to see. So we're gonna get into some more details for that. And before we getting into that, actually, this is like not very common the problem, not only for those cases, but for many other the cases. So we are not gonna get into some too much details about the shape alignment, but actually there are some kind of the many the cases that we want to basically align some kind of the two same shape in terms of like finding some kind of some rotation in the translation. So like one typical example for those kind of like the shape alignment is that when you scan some kind of the 3D shape using the 3D scanner, then we're gonna get some kind of the lots of the point cloud that are captured from the different viewpoint, right? So which means that we are basically capturing some kind of the 3D shape into the point cloud while having some all different the rotation and the translation. And since we can only observe some kind of the partial, some visible area for the 3D shapes from each of the perspective, if we want to basically make some kind of the complete 3D shape, we need to basically align all those kind of some partial scans into the same the rotation and the translation. for those cases, we also need to solve this kind of the problem, like finding the optimal the transformation in terms of that we can align some kind of the two different some kind of the 3D shape for the same object, but with the different some kind of rotation in the translation. So given the cases that we are having some kind of we know some kind of corresponding points in the two different shapes. Let's say like those corresponding the points are basically xi and the yi here. And somehow if we have some kind of the weight for each of some kind of the corresponding the point pair, the problem becomes basically finding some kind of the optimal the rotation and the translation in a way that we are basically minimizing the distance between the corresponding the points. So this is the problem which is called the shape alignment. You can say that actually this is basically solving exactly the same problem, right? And actually this is even more the general problem that only we can see in the geometry processing, but also in the many other fields as well. And this problem is actually called the orthogonal the Procrustes problem, which is named after the Procrustes, which is some kind of the person which is shown in the Greek myth. Have you heard about the Procrustes in the Greek myth before? Anyone who have heard about the Procrustes? No. So Procrustes is the person shown in the Greek myth, and who was the son of the Poseidon. But actually, the Procrustes is kind of like the crazy person. It's like serial the killer. What he used to do is that he invited every some kind of some passing the traveler to his house to spend a night in his house. And after that, like in the night, like he's basically tying the guest's body on the bed, like this. You can see in this slide. And if the body is basically the taller than the bed, and then cutting off the body like this, and then if the body is like shorter than the bed, and basically stretching the body to fit the body to the size of the bed. So he is like known as some kind of the serial killer, somehow like fitting the guest body into the bed. So named after these kind of the things, like the some people in the 1960s somehow basically started to call this problem as kind of the orthogonal the Procrustes the problem in terms of that we are finding some kind of the rotation the matrix while fitting the matrix to be orthonormal the matrix and also making the determinant to be the +1. So actually, this problem has shown in the literature, not only in the geometry processing, but many other fields, even from the 1960s. And people started looking into basically how we can solve this problem for many of the applications. So you can see that this problem is shown in the many other fields, especially including the robotics and some medical imaging the analysis, and also the many other fields as well. So this is like very fundamental the idea, and we are going to get into slightly more details about how we are exactly going to solve this. Okay? And for more details, if you are interested in, I also strongly recommend you to check out this document here, which is called the least scarcity rigid motion using the SVD, and we are also going to get into some more details here. Okay? So actually, let's go with some kind of easier thing first. Okay? So now we are basically optimizing this function with respect to the rotation and the translation, right? So let's think about that. Now we assume that the rotation is given. So we only basically find the optimal the translation here, t, for the given the function here. So how can you find the optimal the translation for the given t here, while we assume that the rotation is basically given? So when the rotation is given and we only find the translation, this problem becomes quite easy. So you can try this, okay? So let's quickly just try this for the 3 minutes. Did everyone get the same answer with this? So this is like kind of easy practice in terms of that you just need to take the gradient of the function with respect to the translation here. And then you can basically rewrite all the formulation that you can see that actually the optimal the translation can be computed based on the weighted the center of the x and also the weighted center of the y here. and then taking like y minus the rx like this, right? So yeah, becomes like very simple deformulation like this. So this is kind of like the easy task, right? You just need to like compute the gradient and just like find the translation that makes the gradients to be 0, right? So this is the case that when the rotation is basically given, right? So now let's like plug in this optimal translation into the original deformulation and say that now the formulation becomes like this. So now we only have the formulation with respect to the rotation here. And you can see that this x hat and the y hat are basically the centralized points, which means that we are translating all the x points and the y points in a way that they're the weighted, the center becomes the origin, right? So after basically taking some kind of the centralized the points like this, now the problem is that how we are going to find the rotation here, which is exactly the same problem that we have seen in terms of defining the rigidity in the previous slide, right? And for that, let's do the same thing. Just like matter of taking the gradient again. So in terms of that, now we are going to rewriting the formulation like this. Then we can say that actually we don't need to care about like those two terms, which is not involved in the rotation, right? So we want to take the minimize this term, and we're just flipping the sign here in terms of now we are maximizing this term like this. Okay. So the whole problem becomes like how we are going to find the rotation R here, which is basically the maximizing here. And for convenience, is this clear? Okay. Yeah. Okay. So just for the convenience, what we are going to do is that we are going to write this equation into the matrix form. So let me define this like the big W and Y and the X, the matrices. And basically the X and the Y matrices are basically sticking the coordinates as kind of a column like this. Right? So we are basically sticking all the coordinates of the endpoints here as the column like this. That becomes the X matrix and the Y matrix. And then we are also defining a diagonal matrix where we are having some kind of all the wedge terms here. Then what we can see is that when you basically compute the multiplication, like all those for the matrix like this, and taking the sum of the diagonal here, that becomes like identical with like computing this part, right? So you can see that this is basically nothing but we are rewriting the same deformulation into the matrix form while just taking the sum of the diagonal at the end, right? So taking the sum of the diagonal is basically the same as by definition is basically the trace of the matrix. So basically trace is basically the sum of the diagonal, right? Like this, right? So this is basically nothing but we are rewriting all the things into the matrix form and using the trace here. And it looks like some kind of a very redundant computation because we only need to take some kind of the diagonal part here. We are not going to use any of the off diagonal part here. Then why do we need to have this kind of the matrix multiplication? Okay. So the reason that why we are going to have this kind of the matrix representation is that there is actually quite interesting the property for the matrix trace. So when you compute the trace of the multiplication of the A and B, and also the trace of the B and A, actually these two outputs are the same. So while the matrix multiplication is not commutative, so if you switch the order like these two, then the output should be changed, right? But if you just compute the trace of the matrix multiplication, whether you take the multiplication of the A and B or the B and A, after taking the trace, the output becomes the same. Okay. So we are going to use this fact in terms of rewriting this the formulation, like multiple more times. So let's say now we are taking this like x, y, w, y transport here, and the rx, these two are some kind of the two matrices. So like w, y transpose, this is like the one matrix, and the rx, this is the another the matrix. And we are going to switch the order of these two in terms of that now we are making r times like x times like w times the y transpose. So you can see that this is nothing but we are switching the order of like these two, right? Then what we can say is that now we are having the rotation here, which is like what we want to get here, right? while basically having the another some kind of the three D matrices, which multiplication can be computed using the information that we have, right? So we're gonna get into that, like why we are switching the order like these two. So let's say like the S basically denotes the multiplication of the X and W and the Y transpose here. Then what's the dimension of the S here? Can you see like what's the dimension of like S? You first need to check out the dimension for the dimensions for the X and the Y and the W, right? So what you can basically see is that X was the basically here. X was the 3 by n matrix, right? Y is also the 3 by n matrix, and the W is the n by n matrix, right? So if when we compute this whole the matrix becomes like the n by n matrix, right? It's basically very big matrix. So after we switch the order of those like the matrices, what you can see is that X was the 3 by n, W was the n by n, and the Y transpose is basically the n by 3, right? So the S matrix becomes like 3 by 3 matrix. So you can see that somehow all the matrix in the multiplication becomes like much simpler in terms like having one 3 by 3 matrix and then having another 3 by 3 matrix, right? Basically, the computation becomes like much simpler in this case. So now we can see that it's the matter of like just computing the trace between the multiplication of the R and the S here. Then still the problem is that how we are going to find some kind of optimal R, which is basically maximizing the trace. So for that, one more thing is that as we have done in the previous lecture, we are going to use the singular value decomposition again in terms of like basically decomposing this 3 by 3 matrix S into the U sigma V transpose. Right? And by definition of the SVD, this U and the V will be orthonormal D matrix, right? While this sigma will be the diagonal D matrix. And we can apply the same trick in terms of like switching the order of the matrices in the inside the trace. So now we are taking this R times U and the sigma times V transpose as like 2D matrices and switching the order like these, like the two the matrices. Now we are getting this another form of the trace. Make sense? So now we can say that the trace form becomes like sigma times V transpose times R times U. And here the reason why we are also doing this kind of like reordering is that what we can say is that V transpose times R times U, these are basically all the orthonormal matrices, right? So we are having the sequence of these diagonal matrix and the three orthonormal matrices. Clear? And then what you can see is that for the V transpose R times R times U, since each of these are the orthonormality matrix, the multiplication of like all those three matrices also should be orthonormality matrix as well. So we are basically now having some kind of the one diagonality matrix and one orthonormality matrix here, which is making the computation even further like simpler, right? So again, what's the dimension of the matrix M? Obviously, the dimension of the matrix M should be another 3 by 3 matrix, right? Because like each of like all those three matrices is a 3 by 3 matrix. So what we have seen is that we are basically computing this to find a rotation D matrix, which is basically the maximizing this term, right? And then we are basically simplifying this computation into the trace of like these two D matrices. One is the diagonal D matrix, another is basically the orthonormal D matrix, right? So this becomes the problem that we are basically maximizing this term, right? Because the sigma is the orthonormal D matrix. So here the question is that how can you choose the rotation the matrix R here in terms like maximizing this, right? So before that, let's think about like we are choosing some kind of the matrix the M here in terms like maximizing this. Then when would the term would be maximized? So basically we want to maximize each of the diagonal term here, right? in terms of the weighted sum of like those becomes of the maximized, right? So what is the maximum value of the the diagonal the elements here for the matrix M here, and when it happens? So here the thing is that we know that this matrix M should be also numerative matrix, right? So based on that, what we can see is that any of the element here should be in the range from the -1 to the +1, right? Because the number becomes greater than the +1, while the smaller than the -1, then the norm of each of the column and the row will not be 1, right? So any of the value here cannot exceed the range from the -1 to the +1, right? So which means that the maximum value for the diagonal term here becomes 1. So let's say like we set 1 for all the diagonal terms here. Then what should be the other terms? The other term should be 0 because like otherwise it cannot be the orthonormality matrix, right? So the norms of each of the rows and the columns should be 1. So if we set the diagonal terms to be 1, then all the other terms should be the 0. So basically, this means that the trace of like these two, the matrix multiplication becomes maximized when the M becomes the identity matrix, right? So we can say that the condition to basically maximize the whole the expression is the case that we are making the M to be basically the identity matrix. And based on that, now we can consider the best rotation, right? What's the best rotation? So we are basically finding some kind of the rotation R, which is basically satisfying this condition. And we know that the V and the U are the orthonormal matrices, right? And based on that, what we can say is that actually the optimal rotation R should be V times U transpose, right? Makes sense? Given that the M should be identity matrix. So yeah, it sounds like the optimal rotation should be V times U transpose, right? The problem is that this is only the case that like when we only basically want to when we know that the M is the orthonormality matrix. But actually there are some cases the V times U transpose may not be a rotation matrix when it's such kind of the case because we know that the V times U transpose always becomes a orthonormality matrix, but the determinant of this matrix may not be +1. There can be a case that it becomes actually the -1 as well. So that's kind of the problem. So as like one thing we can do for handle this kind of the case, then if I just go quickly with this part, is that actually we are finding this kind of the matrix M, which is basically the maximizing this, right? So we want to find any kind of the matrix M, which is maximizing this. But the thing is that if the determinant of the V times U transpose is basically the -1, if there is such kind of case that the determinant of the V times U transpose is basically the -1, we know that the determinant of the rotation the matrix should be the +1, right? So given these two conditions, what we can say is that the determinant of the matrix M also should be the -1 as well. So we need to also consider this condition as well. So M is basically the orthonormality matrix, and the determinant of the V times of the U transpose is the -1, and also the determinant of the M also should be -1 as well. And if we also consider this kind of extra condition, then some kind of the matrix, which is basically maximizing the whole the trace term here, is the case that we are having the +1 and the +1, but not the +1 here, but the -1 here. So this is kind of the optimal, some kind of the matrix, which is maximizing this trace term while making the determinant to be not the +1, but the -1 here. So this is kind of some extra case that we need to handle. So given all those kind of things, what you can see is that actually the optimal rotation the R here can be computed by taking the SVD and the V and the U matrix here, and then basically computing the final rotation matrix like this. So we are basically deciding the sign of the last element over here based on the determinant of like the multiplication like these two. So this becomes the final, the optimal rotation. So it was kind of like quite complicated in terms of how we find the rotation matrix. But actually, in terms of the implementation, it's actually quite simple. So all you need to do is basically computing some kind of the covariance matrix, the S here, and then computing the SVD for this like 3 by 3 matrix, and then basically computing the optimal rotation in this way. Basically computing the multiplication of the V and the U transpose with some kind of the matrix here, which last element is determined by the determinant of the V times the U transpose. Right? Just like few lines of the code. But also you can see that there's some kind of the complicated least scarce problem with the condition that the matrix should be the rotation of the matrix. Actually can be solved without any kind of the fancy tools, but just using the SVD, right? So now we are seeing that how we can find some kind of the optimal rotation in terms of like, aligning some kind of some local neighborhood, right? Any questions on this? So I'd like to recommend you to check out some more details in the slides, because this is not just the problem for the deformation, but this is really the problem that you can see in many other applications as well. So coming back to the local rigidity, which means that if we know some kind of the deformation for the mesh, then for each of some kind of the local neighborhood, we can find some kind of the optimal rotation to represent everything as some kind of the single kind of the rigidity transformation. But as we also have seen in the previous slide, typically we also have some kind of the weight term here for each of the edges connecting to the two vertices. There are also lots of the kind of the options in terms of which kind of the weight that we're gonna use. But some kind of the typical kind of the choice for the weight for each of the edge is this kind of the quantity, which is basically computed based on so when we consider the weight for this edge, we see the angles opposite to this angle, basically this and this, and taking the cotangent of like those two angles and computing this quantity. So it looks like some kind of very random number, right? Why we are taking some kind of angles in the opposite, the opposite angles from the edges and taking the cotangent for those kind of things, right? So this is kind of some very typical choice for the weights. It doesn't need to be this weight. But let me briefly get into like why we consider those kind of the numbers here. So the basic ideas here is that we discussed some kind of the Poisson the ideas in the previous lecture. The Poisson surface reconstruction and the Poisson image editing, which is like all based on basically doing some kind of the editing or with some kind of the reconstruction of the 3D shapes or the 2D images based on some gradient operation and also the Laplacian operator, right? So we have seen some kind of the basic idea in terms of how we can also represent this kind of the first order derivatives and also the second order derivatives, those kind of the operator as some kind of the matrix form in the discrete space. So the basic idea for the one-dimensional case is that we are dividing the space into the uniform interval. Then we are having some kind of the n number of the points in the space. And also a function over the space was represented as kind of the vector, right? By evaluating the function for each of some kind of the point in the interval, right? So what we have seen in the previous lecture is that a function is represented as a the vector, and the operator, like the first derivative operator and the second derivative operator, are basically represented as the matrix, right? So based on that, we can do many kind of things like surface reconstruction and image editing, kind of like many things. Here, the basic idea is that we can do the same thing, not only for the function defined in the 1D, 2D, 3D Euclidean space, but also function defined over some kind of the arbitrary surface. So here the basic idea is that now we are going to treat each of these 3D surface not as just kind of the data, but actually some kind of the domain. We can define some kind of the function over it. So as you can see in this figure, we can define some kind of some function that is taking the surface, some arbitrary 3D surface as kind of the domain for the function. So as we have done in the Euclidean space, we also sampled a bunch of the kind of the points over the space and evaluated the function over those kind of points. Then we are basically representing the now function as some kind of discrete the vector, right? Actually, we can do the same thing for the function defined over the 3D the surface as well. So the 3D mesh can be considered as some kind of discretization of the 3D surface, right? With the n number of the vertices. And if we evaluate any function for each of the vertex over the surface, then we also have the vector representation for the function defined over the surface. Right? So as we have done some kind of the Laplacian based, some kind of the editing, reconstruction kind of things, we can do the same thing for the functions defined over the surface, which means that as we also represent the function as the vector in this space, we can also consider defining some kind of the matrix, which is basically becoming some kind of Laplacian the operator over the surface. So this kind of the generalization of the Laplacian the operator, defining the Laplacian the operator, not for the function in the Euclidean space, but the function over some kind of any arbitrary the manifold, is called the Laplace the Beltrami operator. Yeah, basically same kind of the Laplacian the operator, but for the functions defined over the surface. And while skipping all the details about exactly how we can really calculate this kind of the Laplacian the operator over the 3D mesh, if we see just kind of the results, like how exactly this kind of operator is basically defined, then the Laplace the Beltrami operator over the 3D mesh is defined as this kind of the matrix demultiplication. Here, basically, the M is basically the diagonal the matrix, which is defined with some kind of the area for the vertex. So basically, the area for the vertex is defined like this. You can simply approximate the area for the vertex as kind of the sum of the area of the neighbor the faces and taking the 1/3 of the sum of the face areas. It's kind of like very simple kind of the approximation. Basically, the M is basically defined based on some kind of the vertex area as kind of diagonal matrix. And the L matrix here is defined as kind of the sparse, the cotangent, the weight matrix, which is defined like this. So you can see that actually the quantity that we have seen in the previous slide, which is defined with the cotangent with the angles here, is actually the weight matrix that is being used to define the Laplacian the operator for the functions defined over the surface. So this is basically some kind of definition for the Laplacian of the operator for the functions over the surface. And actually, this kind of the Laplacian the operator for the 3D mesh has lots of the applications. So we also don't have time to discuss all the things. Actually, we can discuss many other things for those in terms of the applications for the operator. Like one interesting aspect for this is that we can do some kind of the spectral analysis for the functions defined over the 3D shape. Does everyone know about the Fourier transform? Is everyone familiar with the Fourier transform and some of the basic ideas there? Yes or no? So what I'm talking about, some kind of spectral analysis here, is that as we do some kind of the Fourier transform for the signal defined in the Euclidean space, we can do the same thing, the Fourier transform for the functions defined over the 3D shape. And the basic idea is that basically the Fourier transform is basically representing all the function as the linear combination of the basis functions, right? And what are the basis functions? The basis function are basically the sine and the cosine. And actually the sine and the cosine, these are basically some eigenfunctions of the second derivative of the operator, which means that if you take the second derivative or like those functions, you can see that it becomes the same function multiplied by some scalar value, right? So that is basically the definition of the vectors and the eigenfunctions, right? So actually the sine and the cosines are basically some kind of the eigenfunctions of the second derivative operator, which means that for any kind of the domain, any kind of space, if we can define some kind of a second derivative operator, basically the Laplacian the operator, and if we can find some kind of the eigenfunctions for those kind of the Laplacian the operator, we can use that as kind of the basis functions for the Fourier transform. So that's the basic idea. So here, basically, we are representing the Laplace the Beltrami operator as kind of the matrix, right? So the eigenfunctions also become some kind of the eigenvectors in these discrete representations. So just by taking the eigenvectors for the Laplace the Beltrami operator, the matrices, we can basically compute these kinds of the eigenfunctions like this. And based on these kind of like the eigenfunctions, we can do all the things about the spectral analysis as we have done for the 1D, 2D, 3D case. For example, like the most kind of the popular example for the transformation might be some image compression. So once we do some kind of the conversion from the image into some kind of the spectral domain using the Fourier transform, if we only take some kind of the coefficients for the kind of the low frequency the basis function and recover this back into the original the image into the image space like this, then you can see that it contains almost the same information while losing some very small the fine details that people cannot tell exactly some of the difference, right? So this is the very basic idea in terms of doing some kind of the image compression, that we are basically sending all the 2D information into the spectral domain and taking only the kind of coefficients for the low frequency the basis function and just going back into the spatial domain again, right? So this is the basic idea for the low pass filtering, and we can do the same thing in the surface in the function over the surface as well. So these are some examples that we are taking the x, y, z coordinates for each of the vertices as kind of the function defined over the shape. And then we are taking some kind of the low pass filtering for those kind of x, y, z coordinates in terms of that we are basically getting some like smoother the shapes like this when you only take some kind of the low the frequency information for the shape. So this is kind of the side note in terms of this like Laplace the Beltrami operator has some kind of lots of the applications for the spectral analysis, and it can be also used to find some kind of some corresponding points across the shapes, and also to compute the distance for the 2 points over the surface as well. So there are tons of the applications. Well, we are not going to have time to discuss all the things. So the basic idea is that the weight, the typical the weights that we are using to compute the optimal rotation in the deformation is basically coming from this kind of the idea for the Laplacian operator. So that's the basic idea. So based on like all those kind of the basic idea, if we coming back to the era of the deformation, basically our goal was to basically find as locally rigid as possible the deformation while basically satisfy some kind of the given the constraints, right? So we want to basically fix all the vertices in the gray area here while moving the yellow the vertices into the upward, while basically making some kind of the locally rigid deformation for all the middle area here in terms of choosing the vertex positions for the light blue area here, right? So that becomes like this kind of some complicated the optimization the problem in terms of that we are basically like minimizing this with respect to both the positions of all the vertices and also the rotation defined for each of the vertex. So we want to basically minimize some kind of some kind of the stretching, some other kind of fact in terms of that all the local deformation is represented as like the single rotation, while also choosing all the vertices, the positions of the vertices like this, while satisfying some kind of the given the condition. So here the question is that how we are going to solve this kind of the optimization. And as we have done in the orthonormal the pro-cross test the case, what we are going to do is that we are going to take some kind of the alternating kind of scheme in terms of that we fix the rotation first and then optimizing the positions. And then we also fix the positions and then also optimize the rotations. So otherwise it's basically too complicated kind of optimization. Sorry. So here the question is that when you do this kind of the alternation, like fixing the rotations and optimizing the positions, and also fixing the positions and optimizing the rotation. Actually, in the previous slide, what we have seen is the second part. Right? Once we basically fix the positions of all the vertices, now we know how we can find the optimal rotation, right? So this is basically done by solving the orthonormal the Proscrotis the problem for each neighborhood, right? So we know how we can do this, right? So the question is that how we solve the first part, right? So actually solving the first part is kind of like not very difficult. It's the same thing that we have done in the previous slide. We just need to take some kind of the gradient of the all the formulation with respect to each of the position of the vertex. And after like rewriting all the formulation and cleaning up, what we get is that we end up getting like this formulation, like this. And also this formulation can be rewritten into a simple the matrix form. The matrix form becomes basically this. So since we defined the Wij, the weight, as some kind of the cotangent value that we have seen in the previous slide, we can see that when we represent all this formulation into the matrix form, we can see that actually the weight term here becomes some kind of the L matrix, which is the cotangent, the weight matrix that we have seen in the Laplace-Beltrame operator. So we just need to compute the vector B here, which is defined in this way. So which means that once we basically, so L is some kind of the given the mesh information. So it does not depend on the some kind of the given the condition. So for the given the mesh, we can compute the L, and then we can also compute the B based on the given the current the rotations for the all the vertices. And we just need to this kind of linear system here, right? But also the thing is that we are not only having this linear system, we have some kind of the given the linear the conditions as well. So let's say like S is some kind of the some selection the matrix, which is basically deselecting some of the given the vertices in a way that we can give some kind of condition that those vertices should have like this position. So here the question is that how we are going to solve this kind of like linear system with this kind of given the linear the condition. And if you took the optimization the course, at the end of the day, like what we are seeing is that it becomes like this kind of the some extended linear system with some kind of the, so L is the matrix, which is the cotangent the weight matrix, and S is the selection the matrix, and then we are basically having some kind of the other some kind of parts here. So it's kind of the complicated, but what you can say is that the basic idea is that we are starting from some kind of initial the positions and the rotations, and then we are repeating these two. So while fixing the rotations, we solve the linear system to find the optimal the positions of the vertices. And based on that, we also find the optimal the rotations like this. And we are iterating these two in terms of like basically getting converged into some kind of the more natural deformations. So these are some kind of the examples that we are basically fixing the red point here and then moving the yellow point here. So as we basically iterate more, solving those kind of two systems, you can say that we are seeing some kind of the more natural, some kind of the deformation like this. So this is some kind of the starting from some kind of initial deformation. As we iterate more and more, we are seeing some kind of the more natural deformations like this. And the good thing like this kind of the idea is that this is kind of the some iterative method, which means that if we start from some kind of the good some deformation, then we can converge faster. So this can be especially good for some kind of the interactive some deformation, because like we can start from some kind of deformation from the previous frame, and then basically making some kind of the further the refinement with some kind of the more the manipulations by the user as well. So we can see some more interactive some deformation the demo as well. So this is the demo which is created by some kind of the by Pengyu Hui, which is the graduate student in the UC San Diego. So he made some kind of really nice demo here. And actually, you can play this yourself. So I just open up the things. So in this web page, what you need to do is that you just like fix some part like this, and fixing this part, and also fixing this and the part. Let me pick this part. And if I just move point like this, then you can see some deformation like this. You can see that the yellow, the vertices are basically fixed. And then when I move the red vertices like this, then all the points are basically moving like this. So the reason like why we can achieve this kind of some interactive deformation is that the computation is actually quite fast. As you can see, like the orthogonal the properties, the problem is basically solving the SVD for the 3x3 matrix for all the vertices, but that can be parallelized because like everything's like independent, right? And also for the optimal the positions, we can basically precondition the big matrix in terms of that we can solve the linear system much faster. So you can see that this kind of deformation can be computed in real time. Clear? Any questions on this? So Yeah, this was like very specific the idea in terms of like how we can utilize the mesh representation for the manipulation. And as I mentioned at the beginning of the lecture, there are lots of techniques about how we can do some kind of the mesh deformation. I just wanted to introduce like one specific idea, which is actually the most popular the technique that has been used for the many the applications. Okay, so that's it. So this was about the some mesh deformation. And the last lecture on this, like coming Wednesday, we are wrapping up all the discussions in this course. And as some kind of some last the topic, I'm going to briefly talk about some 3D generation and some other the topics that we haven't discussed in this course yet. So we are going to wrap up the course, and then we are going to move on to the project presentations. Any questions on this? And as I said, we are going to have the Wednesday lecture offline. So please come to the class soon so that we can also discuss the future plans for the project presentations. So I will see you on next Wednesday. Thank you. Bye.